Hello, this is Thai from Institute Education. In this video, I'm going to help you to solve a question in IB Physics Paper 2 HL May 2019, Time Zone 2. This is question 3 about waves and sound. The diagram shows the direction of a sound wave traveling in a metal sheet. Question A. Particle B in the metal sheet performs simple harmonic oscillations when the displacement of P is 3.2 micrometers. The magnitude of its acceleration is 7.9 meter per second squared. Calculate the magnitude of the acceleration of P when its displacement is 2.3 micrometers. Question A asks us about the magnitude of acceleration of the oscillation of the particle P in this metal sheet. And in this question, we do not need to care about the diagram. The diagram indicates the transfer of a wave in that direction along this line. But that is for other question, not for question A. The question A is just about acceleration, and we know when the displacement is 3.2 micrometer is 7.9 meter per second square, and the question is the magnitude of acceleration when displacement is 2.3 micrometer. So we know that there must be a relationship between acceleration and displacement, and that relationship is in the section of simple harmonic motion. We have that the acceleration A is proportional to the displacement, denoted by the equation A equals minus omega squared times x, with x is the displacement and omega is the angular frequency. And the graph, just to note so that you remember this equation and this relationship. If we plot the graph of displacement x on the horizontal axis and the vertical axis acceleration, then the graph is a line passing through the origin and with the negative gradient like that. And so when the displacement is 3.2 micrometer, we have the acceleration is 7.9 meter per second squared. Now the displacement is 2.3 micrometer. The question is what the new acceleration? It is simple, right? A proportional relationship. So A is 2.3 over 3.2 and then multiply with this acceleration 7.9 equals 5.7 meter per second square. The question A is done. Okay, let's move on to question B. The wave is incident at point Q on the metal-air boundary. The wave makes an angle of 54 degrees with the normal at Q. The speed of sound in the metal is 6010 meters per second, and the speed of sound in air is 340 meters per second. Calculate the angle between the normal at Q and the direction of the wave in air. Let me remind you about the refraction of wave when it passes through the boundary between the two media. We are probably familiar with the refraction of light. For example, if it is light coming from the air to the water, for example, water, okay? This is the light ray. Do you remember in which medium the light travels faster? Yes, it is in the air. Light travels faster, and in the water, light is slowed down. This is the incident angle, the angle that the light ray makes with the normal line. the incident angle in the air is greater than the refracted angle in the water. This is the refracted angle R. The Snell law for light states that the refractive index N1 of the incident medium times sine of the incident angle I equals the refractive index N2 times sine of refracted angle R. But now for the sound. Now we have sound. This sound goes from a denser medium, which is a metal sheet, which is solid, to the air in this direction. Just remind you about the statement of the problem, okay? In the solid, the sound travels faster, a lot faster, and in the air it travels slower. And the problem state that the incident angle is 54 degrees. And similarly to the light, it goes to the air and refracted and make a small angle. This is the refracted angle, similar to the light, okay? And I intentionally draw the angle are extremely small. Why? Because the speed of sound in the metal is a lot greater than in the air. Here in the metal, its speed is 6010 meters per second, and in the air it is just 340 meters per second. So a lot difference. Now, similar equation for the light. The relationship between the speed of the sound in the two media and the angle. We have sine of the incident angle, which is 54 degrees, over the sine of the refracted angle R, which we have to find, must be equal to the ratio of the faster speed and the slower speed. The faster speed is 6010 meters per second and the slower speed is 340. So we can calculate the angle from this equation, right? The angle R is approximately 2.6 degrees, a lot smaller than the incident angle. That is how we answer this question. Okay, let's move on to question 3. The frequency of sound wave in the metal is 250 Hz. Determine the wavelength of the wave in air. This is simple, right? We have to determine the wavelength lambda, and the equation for the wavelength is speed v over frequency f. The speed in the metal, the frequency of sound wave in the metal, okay. The speed in the metal is 6010 meters per second, and the frequency 250 hertz. Hertz means per second. Okay, so this ratio gives 24.01. The two number behind the dot is extremely small and it's not significant, so I can round it up to two significant figures. 24 meter, that's the wavelength. Okay, the other part of the question, determine the wavelength of the wave in the air. It is similar, just the same equation, but now the speed in the air and divided by the frequency. The frequency is always the same, 250 Hz. Doesn't matter it is a sound wave or light wave, the frequency doesn't change. The only thing that different is the speed. Now, the speed in the air is 340 meters per second, and this ratio is 1.36 meter and drag it up to 1.4 meter to get two significant figures. Okay, that is the difference in the wavelength. In the metal sheet, the speed is a lot faster and therefore the wavelength is a lot longer than in the air. Question D. The sound wave in air in sea enters a pipe that is open at both ends. The diagram shows the displacement at a particular time t of the standing wave that is set up in the pipe. You see the diagram here. This is a node and this is an antinode. A particular air molecule has its equilibrium position at the point labeled M on the diagram at time t. Draw an arrow to indicate the acceleration of this molecule and label this with the letter C at a point in the pipe that is at the center of compression. The first thing you have to know very carefully about this question is that the meaning of this diagram, it is the displacement of the molecules. So this is at an instant, at a certain time, a particular time t. Of course, the particles in the pipe oscillate back and forth, and the displacement of each particle at different time are different. To answer this question, we have to understand how the molecules in the pipe move and how does it relate to this diagram. Let's look into this simulation carefully. In this simulation, we have the two pipes on the top and at the bottom here, which illustrate the movement of air molecules. On the top pipe, we have two waves, the blue one and the orange one, which indicate the incident wave traveling like from the left to right and the reflected wave traveling back from right to left. And when the condition is satisfied, the resultant of the two waves result in the black wave, the standing wave at the bottom tube here. So we see that the standing wave individually, the orange or the blue particle, they oscillate back and forth. Now let's look carefully into the bottom. Note carefully on the node position. You see here the particle here, which means these particles along this vertical line doesn't move at all. They are at rest. This is a node, and all the particles on the two sides of this node oscillate back and forth. Each particle has certain displacement. For example, consider these particles on the vertical line just next to a node. You see? They are moving with the same phase, or to the right or to the left, with a very small displacement because it is very close to the node. Now, consider these particles on the antinode on the vertical line. They oscillating with the greatest displacement, because that is where the antinode is. So what I'm trying to say is that depends on the position of the particle on the node or antinode or any other position along the standing wave. Each particle has different displacement. When the diagram like this, like in the state of the problem, the particles indicated by the positive displacement above the equilibrium, they are moving to the left. So according to the simulation, all the points with positive displacement must move to the left so that they go to the equilibrium, including the point M. So the point M moved to the left, but the question is acceleration. Acceleration A equals minus omega square x, and the minus sign here indicates that the acceleration is opposite to displacement. The displacement is positive and therefore the acceleration is negative, but the direction of accelerations is always toward the center of the oscillation. So the point M moves to the left to the equilibrium position, and the acceleration also moves to the left. So this is the answer. Okay. Now, question 2. Label with the letter C on a point in the pipe that is at the center of compression. The center of compression is at a node, which means that any point along this vertical line at one node is the compression. To see that more clearly, look at the simulation again. This is this point at a node. Now look carefully. When these particles on the left and the right compress, move toward these equilibriums, these nodes. So this is a compression region in which the point here, a node is the center of compression. So the answer to our problem is all the particles on a vertical line passing through the node of the standing wave. The final part of this question, question E. Sound of frequency f equal to 2500 Hz is emitted from an aircraft that moves with a speed of v equal to 180 meters per second away from a stationary observer. The speed of sound in still air is c equal to 340 meters per second. Calculate the frequency heard by the observer and the wavelength measured by the observer. So when reading a problem about sound frequency and the movement, approaching an observer or moving away from observer, we will think of Doppler effect. Doppler effect is the change in frequency of a wave. It could be sound wave, it could be light wave. That is the change of the frequency because of the movement, because of the velocity of the sound source or the receiver. And we remember that when the two things, the source or the receiver, approach each other, the frequency f increases. And when the source or the receiver get away from each other, the frequency decreases. That is very important to remember. The equation for Doppler effect is that the Doppler frequency Fd equal the stationary frequency, then multiply with the speed in the medium divided by that speed plus or minus u, which is the relative velocity between the two things, the source and the receiver. The negative sign is when they're approaching each other, so that the bottom number is less and therefore the frequency gets higher. So in this case, of course, we will use the negative only, the negative, the minus sign, because they are approaching each other. And in this case, the airplane is moving away from the observer. So we will use the plus sign instead of the minus sign. Now, plug the number into this equation. The frequency heard by the observer is 2500 Hz multiplied with the speed 340 meters per second, then divided by 340 plus 280 meters per second, and the result is 1371, or I can round it up to 1400 Hz. And the final question, wavelength measured by the observer. That wavelength lambda is calculated by the speed divided by frequency measured at the observer. And this wavelength, note that the wavelength is inversely proportional to the frequency. So when frequency decreases, the wavelength increases, which means that the stationary observer will observe a longer wavelength, which is the speed is 240 divided by the frequency here 1371. The result is 0.25 meters. And that is all the solution how we answer the question 3 related to sound, standing wave and Doppler effect in IB paper 2. Thank you very much, and I hope that if you have any question, leave a comment below. Thank you and see you next time.